Hello everyone, I am Sham Parekh. I am a student of BSc Chemistry Honours first year. My roll number is 10 and today we are going to read the chapter cycloalkanes and cycloalkenes. Cyclic aliphatic hydrocarbons or alicyclic hydrocarbons are hydrocarbons which contain closed chains or rings of carbon atoms and resemble open chain or aliphatic hydrocarbons in many respects. Like aliphatic hydrocarbons, alicyclic hydrocarbons may be saturated or unsaturated in nature. Saturated alicyclic hydrocarbons are generally known as cycloalkanes. They have the general formula CnH2n and are isomeric with alkenes. In this chapter, we shall discuss the chemistry of cycloalkanes and cycloalkenes. Nomenclature of cycloalkanes. Common name. Saturated alicyclic hydrocarbons contain a number of methylene groups joined together to form a ring, therefore they are known as polymethylenes in the common system. Accordingly, the individual members are named by prefix the number of carbon atoms in the ring before the word methylene. For example, trimethylene, tetramethylene, hexamethylene. IUPAC system. In the IUPAC system, the saturated alicyclic hydrocarbons are termed cycloalkanes. The individual members are named by adding the prefix cyclo to the name of corresponding straight chain hydrocarbon having the same number of carbon atoms as the ring. For instance, cyclopropane, cyclobutane, cyclohexane. Quite often, alicyclic hydrocarbons are also represented by drawing simple geometric figures such as triangle for cyclopropane, a square for cyclobutane, a pentagon for cyclopentane, and so on. The presence of carbon atoms at each of the corner and hydrogen atoms attached to carbon is taken for granted. For example, cyclopropane, cyclobutane, cyclopentane, cyclohexane. Nomenclature of substituted cycloalkanes. IUPAC names of substituted cycloalkanes are assigned by following IUPAC rules, which the student has already studied. However, some important points are given below. For monosubstituted cycloalkane, there is no need of numbering to indicate the position of the group. For example, methyl cyclohexane. For cycloalkanes containing more than one substituent, the numbering of the carbon atom of the ring is done in such a way that the substituents get the lowest possible number. Their names are prefixed in alphabetic order along with their position. For example, 1,3-dimethyl cyclopropane, 4-ethyl 1,2-dimethyl cyclohexane, 1-ethyl 2-methyl cyclopentane. As a ring contains equal or more number of carbon atoms than the alkyl group attached to it, the compound is named as derivative of cycloalkane and the alkyl group is taken as a substituent as already shown. If the ring contains lesser number of carbon atoms than the alkyl group attached to it, or if more than one ring is attached to a single chain, the compound is named as derivative of alkane and the alicyclic ring is treated as the substituent. For example, 2-methyl-1-cyclopropyl-butane, 1,3-dicyclohexylpropane. In addition to the above rules for cycloalkanes, some important points for naming cyclic compounds containing multiple bond and other functional groups are: if the carbon chain attached to the alicyclic ring contains a multiple bond or a functional group, the carbon chain is taken as the parent and the ring is treated as a substituent irrespective of the size of the ring. For example, 3-methyl-1-cyclobutyl-but1-ene, 1-cyclohexylbutane-2-on. If a compound contains an alicyclic ring directly attached to benzene ring, it is named as derivative of benzene. For example, cyclohexylbenzene, 1,3-methyl-cyclohexyl-4-nitrobenzene. If the ring contains a multiple bond and the side chain contains a functional group, the ring is treated as substituent and the compound is named as derivative of the chain containing the functional group. For example, 4-cyclohex 2-enylbutane-1-ol. If a functional group containing carbon is directly attached to a alicyclic ring, the carbon atom of this group is suitably included in the suffix used for the group. For example, CHO group is represented by the suffix carbaldehyde, COOH by carboxylic acid and CN by carbonitrile. Synthesis of cycloalkanes and the derivatives. Only method number 3, 5 and 7 are included in the syllabus. The important method of synthesis of cycloalkanes and the derivative are described below. Most of this method, it may be noted, involve the conversion of some open chain compound into a cyclic compound through the process is of cyclization or ring closure. The cyclic compound thus obtained may be cycloalkane or its derivatives. If required, the cycloalkane derivative is further subjected to suitable reactions to change it into the desired cycloalkane itself. Addition of carbenes to alkenes. This method involves the addition of carbene to alkene to form cyclopropane derivatives. The reaction is also referred to as cycloaddition. Since free carbenes are too reactive to be isolated, the reaction is actually carried out by using a carbene precursor that generates the carbene under suitable experimental condition. For example, when treated with diazomethane or ketane in the presence of light, alkenes add on carbene to form cyclopropane derivatives. For instance, 2-butane in H nu, it gives us 1,2-dimethyl cyclopropane. Simmons-Smith reaction. In this method, addition of carbene is carried out by treating the alkene with methylene iodide and ZnCu couple to get cyclopropane derivative. For example, Alkene plus CH2I2 in the presence of ZnCu gives a substituted cyclopropane. ZnCu couple required for the reaction is usually obtained by heating zinc dust with CuCl in ether in the presence of nitrogen. It is believed that methylene iodide and zinc react to form carbene-like species called carbenoid. The carbenoid brings about the stereospecific addition of CH2 group directly to the alkene. Siemens-Smith reaction gives better yield of cycloalkane than is obtained by the addition of free carbene to alkene. Photochemical 2+2 cycloaddition reaction. The term cycloaddition denotes an addition reaction between two unsaturated molecules to form a cyclic product. During this reactions, new sigma bonds are formed at the cost of pi bonds of the reacting molecules. Individual reactions are designated by writing the number of pi electrons of each reactant in a square bracket. For example, the reaction between two alkene molecules to form a cyclobutane ring by using 2 electrons of each molecule is referred to as 2+2 cycloaddition. 2+2 cycloaddition reaction can be carried out easily in the presence of light but not under thermal conditions. Such reactions are termed as photochemical 2+2 cycloaddition reaction. They take place by a concerted mechanism involving cyclic transition state. The formation of substituted cyclobutane by photochemical cycloaddition of two alkane molecule may be represented in general as follow. Alkene in the presence of H nu gives a cycle transition state, and after that it gives a substituted cyclobutane. 4+2 cycloaddition. Diol-Adler reaction. Cycloaddition reactions involve the addition of an alkene, that is 2 pi electron, referred to as diphenol, and a conjugated diene, that is 4 pi electron, to form 6-membered system. In contrast to 2+2 cycloadditions, these reactions take place readily under thermal conditions. For example, 1,3-butadiene plus ethane gives a cyclohexane. If the diphenol contains electron attracting groups such as C double bond O, COOH, C triple bond NCI, the reaction takes place extremely easily, sometimes even at room temperature. For example, 1,3-butadiene plus CH double bond CH2 and CHO in the presence of 373 Kelvin gives us 1236 tetrahydrobenzaldehyde. Dehalogenation of suitable dihalogen derivative of alkanes. Freund's method. On treatment of suitable alpha and omega dihalogen derivatives of alkene, that is dihalogen derivative having the halogen atom attached to terminal carbon atom with sodium or zinc, they get dehalogenated to form cycloalkanes. For example, 1,3-dibromopropane plus zinc gives a cyclopropane, and 1,4-dibromopropane plus zinc gives a cyclobutane plus ZnBr2. The method may be regarded as an internal Wurtz reaction. However, this method gives good yield only in the preparation of cyclopropane. If the alpha and omega dihalide contains more than 6 carbon atoms, intermolecular Wurtz reaction takes place, giving rise to open chain alkanes. Now, Dickmann cyclization. When esters of certain dicarboxylic acids such as adipic acid and pimelic acid are treated with sodium or sodium ethoxide, they undergo intermolecular Claisen condensation to yield cyclic beta ketoesters. The beta ketoesters on hydrolysis and heating get decarboxylated to form cyclic ketones. The ketones are in turn subjected to Clemmensen reduction to get cyclic alkanes. For instance, adipic ester in the presence of Na give us 2-carbeth ethoxy cyclopentanol, and in the presence of H2O and H positive it gives us 2-carboxy cyclopentanol. Dickmann method is most suited to the preparation of 5 and 6 member rings. Pyrolysis of calcium or barium salt of dicarboxylic acids. When the calcium or barium salts of certain dicarboxylic acids are heated strongly, they yield a cyclic ketone. The ketone thus formed is converted into cycloalkane through Clemmensen reduction as illustrated below. Calcium adipate in the presence of heat it gives a cyclopentanol, and in the presence of zinc and mercury and HCl it gives a cyclopentane. In keeping with Planck's rule, this method is used for the preparation of 5 and 6 member ring. Planck's rule. This rule was formulated by Planck on the basis of experimental observation of the ease of formation of cyclic anhydrates and ketones by distillation of dicarboxylic acids according to relative positions of two carboxylic groups. According to the rule, distillation of 1,4 and 1,5 dicarboxylic acid give rise to cyclic anhydrides, while 1,6 and 1,7 dicarboxylic acids yield ketones. 1,8 and high dicarboxylic acid remain unaffected. Planck's rule can be used for determining the size of the ring as well as the chain length of the dicarboxylic acid. For this purpose, a double bond is introduced by suitable method in the given compound whose ring size is to be determined. Now, Thorpe-Ziegler reaction. On heating in the presence of lithium diethylamide C2H52 N negative Li positive and alpha omega dinitrile, that is the dinitrile in which nitrile group are attached to terminal carbon atoms, undergoes intramolecular condensation to form a cyclic iminonitrile. This is changed into cycloalkane as illustrated below. Alpha omega dinitrile gives us aminonitrile, and ketoxide gives us ketone, then after it gives us cycloalkane. The first step in the reaction involving cyclization takes place only at very high dilution. It is referred to as Ziegler high dilution technique. Tropisch-Ziegler reaction is particularly suitable for the preparation of higher ring compounds. Damjanov rearrangement. This reaction provides a method of expanding and contracting alicyclic ring systems through the formation of carbocations. The carbocations themselves are obtained by the dimerization of acyclic amines and by treatment with nitrous acid. Once formed, the carbocations undergo its characteristic reaction, that is, addition of nucleophiles, elimination of a proton, rearrangement to a more stable carbocation. As a result, different products are formed, including ring expansion or ring contraction products as illustrated below. Ring expansion. When cyclobutyl methylamine 1 is treated with nitrous acid, we get 4 products. Cyclobutyl carbinol and methylene cyclobutane are formed without involving any ring expansion. At the same time, cyclopentanol and cyclopentene are formed by ring expansion and ring contraction. When cyclobutylamine is treated with nitrous acid, cyclobutanol is formed without any ring contraction. At the same time, cyclopropyl carbinol is formed by ring contraction. It may be noted that when the carbocation initially formed carries the positive charge on the alicyclic carbon, it leads to ring contraction. On the other hand, when the initially formed carbocation carries the positive charge on a carbon alpha to the alicyclic ring expansion takes place. Hydrogenation of aromatic compounds. Cyclohexane and its derivative can also be prepared by the hydrogenation of benzene and its derivative. For example, benzene plus 3H2 gives us cyclohexane. Condensation of suitable dihalides with malonic ester or it may be noted that when the carbocation initially formed carries a positive charge on the alicyclic carbon, it leads to ring contraction. On the other hand, when the initially formed carbocation carries a positive charge on a carbon alpha to alicyclic ring expansion takes place. Hydrogenation of aromatic compounds. Condensation of suitable dihalides with malonic ester or acetoacetic esters followed by hydrolysis and decarboxylation. In the presence of sodium methoxide, active methylene compounds such as malonic ester and acetoacetic ester condense with suitable dihalides to form cyclic diesters. These on hydrolysis and decarboxylation yield cycloalkanes. For instance, ethylene dibromide plus malonic ester gives us cyclopropane dicarboxylic ester, and upon hydrolysis it gives us cyclopropane dicarboxylic acid, and upon heat it gives us monocarboxylic acid. Cyclopropane monocarboxylic acid is then converted into cyclopropane through a sequence of reactions. It may be noted that this acid cannot be directly decarboxylated by heating, as it leads to cleavage of the ring. Acetoacetic ester may also be used in place of malonic ester in this reaction. Physical properties. In their physical properties, cycloalkanes resemble the corresponding open chain compounds, although they have somewhat higher boiling point and densities. For instance, the first two members of cycloalkanes are gases while higher members are liquids. They are nonpolar in nature and as such insoluble in water but soluble in organic solvent. Some of them, such as cyclohexane, are good solvent themselves. Chemical properties. The general chemical behavior of cycloalkanes is similar to that of corresponding open chain hydrocarbons. Like alkenes, cycloalkanes also contain only carbon-carbon and carbon-H sigma bond and are therefore quite inert toward chemical reagents and undergo only a few substitution reactions. It must be emphasized, however, the cyclopropane and cyclobutane differ considerably from their higher homologues. This is because the cyclopropane or cyclobutane rings are not very stable and have a tendency to open up and form addition products. As such, they resemble alkenes in undergoing some addition reactions, but they are less reactive than corresponding alkenes. A few reactions of cycloalkanes are described below. Reaction with halogens. Generally speaking, cycloalkanes undergo free radical substitution with halogen at higher temperature or in the presence of light. For example, cyclohexane plus Br2 at H nu gives us bromocyclohexane, and cyclopropane plus Cl2 in the presence of light gives us chlorocyclopropane. In case of cyclopropane, however, bromine and chlorine break the ring system in the presence of FeBr3 or FeCl3 and high temperature and open yield chain addition products. For example, cyclopropane plus Br2 in the presence of FeBr3 gives us 1,3-dibromopropane. Reaction with halogen acids. In general, cycloalkanes do not react with halogen acid. However, cyclopropane adds on halogen acids to form open chain alkyl halides. For example, cyclopropane plus Hi gives us N-propyl iodide, and cyclopropane plus HBr gives us N-propyl bromide. Addition of water. When heated with concentrated H2SO4, cyclopropane but not other cycloalkanes adds on water to form an alcohol. For example, cyclopropane plus H2O in the presence of H2SO4 gives us N-propyl alcohol. Reaction with hydrogen. When heated with hydrogen in the presence of nickel, cyclopropane and cyclobutane form open chain addition products while higher cycloalkanes do not react. Reaction of cyclobutane takes place at much higher temperature than required in case of cyclopropane. Cyclopropane plus H2 in the presence of nickel at 353 to 373 Kelvin gives us N-propane. And cyclobutane plus H2 at high temperature gives us butane. It may be noted that of the cycloalkane, cyclopropane is the most reactive since it undergoes many addition reactions accompanied by ring cleavage. Next comes cyclobutane, which undergo addition of hydrogen, while the rest of cycloalkanes do not form addition products. Relative stability of cycloalkanes. During the earlier stage of the study, cycloalkanes containing up to only 6 carbon atoms could be prepared in the laboratory, and the rings containing 7 or more carbon atoms were unknown. It was also observed quite early that, like open chain alkanes, cyclopentane and cyclohexane are quite stable and do not undergo addition reactions. On the other hand, cyclopropane and cyclobutane were found to be relatively much less stable and capable of undergoing even addition reactions through ring cleavage. The difference in the relative stabilities of different cycloalkanes was initially explained in terms of Beer-Strain theory. According to tetrahedral concept of carbon, a carbon atom bonded to 4 other atoms lies at the center of the tetrahedron, and the angle between the two bonds is 198 degree 28 minutes. Adolf von Beer in the 1885 argued that any departure from this position leads to a strain in the molecule, as a result of which the stability of the molecule decreases. On this basis, Beer proposed a theory known as Beer-Strain theory. The important points are: the carbon atoms constituting the rings lie in the same plane. Consequently, the bond angles between the adjacent carbon atoms of the ring no longer remain 109 degree 28 minutes, which is the normal bond angle of a tetrahedral carbon. On the other hand, different rings have different values of this angle. For instance, the cyclopropane ring is a triangle having a carbon angle of only 60 degree. Any deviation, positive or negative, from the normal tetrahedral bond angle of 109 degree in 28 minutes during the formation of a ring produces an internal strain in the resultant molecule, which makes the molecule unstable. The greater the deviation from the normal angle, the greater is the strain, and therefore the lesser is the stability. It may be noted that, however, the sign of deviation makes no difference. The more the stability of a ring system, the more it easily is formed. Beer calculated the deviation from normal angle to what we call as angle strain involved in the formation of cycloalkanes of various ring sizes. For example, the carbon angle of a cyclopropane ring is 60 degrees since each carbon occupies a corner of an equilibrium triangle. This means the angle strain would be 24 degree 44 minutes. Similarly, the carbon angle in cyclobutane is 90 degree, as each carbon is situated at the corner of a square. As such, the angle strain will be 9 degree 44 minutes. The angle strain for cycloalkanes are: for cyclopropane it is 60 degree and angle strain is 24 degree 44 minutes. For cyclobutane it is plus 9 degree 44 minutes, and for cyclopentane it is plus 0 degree 44 minutes. So this was all about our cycloalkanes, and after that we will start about our cycloalkenes or cycloarenes. Now we shall start about what are cycloalkenes. Now we shall discuss about limitation of Beer-Strain theory. Beer-Strain theory failed to explain the following: ease of formation of ethylene bond, stability of cyclohexane and higher cycloalkanes, heat of combustion of cycloalkanes. Now we will discuss about the Skies-Mohr theory of strainless rings. To explain as to why cycloalkanes having rings of 6 or more carbon atoms are almost as stable as cyclopentane, states put forward a theory of stainless rings for higher ring compounds. According to him, carbon atoms constituting the rings lie in the same plane only up to 4-membered ring, while the carbon atom in 6-membered and higher rings do not lie in the same plane. Since the carbon atoms in 6-membered and higher rings lie in different planes, the normal tetrahedral angle remains unaltered, as such that there is no angle strain in bigger rings, and that is why they are stable. For instance, says propose the existence of two types of multiplanar or puckered stainless rings known as chair and boat forms for cyclohexane. Both these forms are free from angle strain and can be interconverted just by rotating around single bonds. Difficulty encountered in the synthesis of a large membered ring. It may be interesting to know as to why bigger rings are rather difficult to synthesize even though there is no angle strain in them. This is primarily due to the fact that two ends of the chain of atom must come close together for ring closure to take place through interaction between the groups present at the two ends. If the chain undergoing ring closure is very long and there are relatively lesser chances of the two ends coming close enough for the ring to be formed. On the other hand, what may happen is that end of one chain may interact with the end of different chain, leading to the formation of an entirely different product. Now we will discuss about the bent or banana bond in cyclopropane, orbital picture of angle strain. According to the orbital concept of covalency, a covalent bond can be formed between two bonds only if these atoms are orientated in such a way that their orbitals can overlap each other. It may also be recalled that the greater the overlapping of atomic orbitals, the stronger the bond formed. Now the carbon atoms of cycloalkanes are in a state of sp3 hybridization and formation of a covalent bond between two such atoms involving the overlap of an sp3 orbital of one carbon with a similar orbital of the other. For maximum overlap, the bonding should take place in such a way that bonding orbitals point directly towards each other. Consequently, when carbon is bonded to two carbon atoms, the CCC bond angle should be 109 degree 28 minutes, but in cyclopropane the carbon bond is only 60 degree. This means that in cyclopropane the bonding orbital are not pointed direct towards each other along a straight line. As a result, the overlap of this orbital take place to a very small extent and bond forms are described as bent bonds. These bonds are much weaker than the normal carbon bond. Consequently, the cyclopropane molecule is quite unstable or strained and reactive in nature. Now, we shall discuss about the method of preparation of cycloalkanes. Cycloalkanes are generally prepared from other cyclic compounds by beta elimination reactions such as dehydration and dehydrohalogenations. By the dehydration of alicyclic alcohols. As in case of open chain alcohols, dehydration of alicyclic alcohols to form alkenes is brought about by heating with concentrated sulfuric acid. For example, cyclopentanol in the presence of H2SO4 and heat gives us cyclopentene plus H2O. 2-methyl cyclohexanol in the presence of H2SO4 and heat gives us 1-methyl cyclohexane plus 3-methyl cyclohexene. More highly substituted cycloalkene. It may be noted that the dehydration of 2-methyl cyclohexanol, that in the dehydration of substituted alicyclic alcohol, the more highly substituted cycloalkane is the major product. By the dehydrohalogenation of alicyclic halides, when treated with bases such as alcoholic KOH, cyclic halides form cycloalkanes. For example, cyclopentyl bromide plus KOH in the presence of heat gives us cyclopentene, and 1-methyl cyclohexene plus KOH, which is in alcoholic form, in the presence of heat gives us 1-methyl cyclohexene plus methylene cyclohexane. Okay. Now we shall discuss about the chemical properties of cycloalkene. Cycloalkenes exhibit the usual properties of alkenes. They undergo electrophilic addition reaction in which the using remains intact. The important reactions of cycloalkenes are given below. Addition of hydrogen. Cycloalkenes undergo catalytic hydrogenation to form cycloalkanes. For example, 1,2-dimethylhexene plus H2 in the presence of PT gives us cis-1,2-dimethyl cyclohexene. It may be noted that the addition of both hydrogens to the double bond takes place from the same side, that is, cis addition takes place. Addition of halogens. Cycloalkenes add on halogen to form dihalocycloalkanes in corresponding to hydrogenation of cycloalkanes. Addition of halogen to cycloalkanes is trans-addition reaction, that is, the two halogens are added from the opposite sides of the double bond. For example, cyclopentene plus Br2 in the presence of CCl4 gives us trans-1,2-dibromocyclopentane. Addition of halogen acids. Like alkenes, cycloalkenes undergo electrophilic addition reactions. Halogen acids, according to Markovnikov's rule, this reaction involves trans-addition. Example, cyclohexene plus HBr gives us cyclohexyl bromide, and methyl cyclopentene in the presence of HCl gives us 1-chloro-1-methyl cyclopentene. But addition of HBr in the presence of peroxide takes place to against the Markovnikov rule and follows free radical mechanism. For example, 1-methyl cyclopentene in the presence of HBr gives us 1-bromo-2-methyl cyclopentene. Addition of hypohalous acid, formation of halohydrins. Cycloalkenes react with hypochlorous acid and hypobromous acid to form trans-halohydrins. For example, cyclopentene plus ClOH in the presence of Cl2 and H2O gives us trans-2-chlorocyclopentanol. Addition of carbene or carbenoids. Cycloalkenes undergo addition or carbene or carbenoids to form bicyclic compounds. For example, cyclohexene undergoes Siemens-Smith reaction with diiodomethane in the presence of zinc-copper couple as shown below. Cyclohexene plus CH2I2 zinc-copper in the presence of ether gives us bicyclo. Hydroxylation. Cycloalkenes undergo hydroxylation on treatment with potassium permanganate KMnO4 or osmium tetroxide to form cis-glycols or diols. For example, cyclopentene in the presence of KMnO4 gives us cis-cyclopentene 1,2-diol. Ozonolysis. Ozonolysis of cycloalkenes resulting in the cleavage of the ring system at the site of double bond forming dicarbonyl derivative with the same number of carbon atoms. The reaction can be used to locate the position of the double bond. For example, allyl cyclohexene in the presence of O3 gives us ozonoid, which on further reaction gives us dicarbonyl derivative. Conformation of cycloalkanes. Due to sp2 hybridization of the carbon atom constituting the double bond of cycloalkanes, these two carbon atoms and the atoms directly attached to them must lie in the same plane. Therefore, for the first two cycloalkanes, that is cyclopropane and cyclobutene, all the ring carbon atoms lie in one plane. On account of large angle strain in them, these molecules are highly strained. Cyclopentane is also supported to the nearly planar but has very little angle strain. In contrast with smaller ring cycloalkanes, cyclohexane and larger cycloalkanes exist in straight free nonpolar or puckered conformation. So this were about the method of preparation and the chemical reaction of cycloalkenes. Now first let us discuss what cycloalkenes are. Cycloalkenes are unsaturated alicyclic hydrocarbons having a carbon-carbon double bond in their molecule. General formula CnH2n-2. They are named by adding the word cyclo to the name of straight chain alkene having the same number of carbon atoms as the ring. The double bond always takes to be located between carbon 1 and 2 and therefore its position need not to be specified. For example, cyclopropane, cyclobutene, cyclopentene, 1-methyl cyclohexene, etc. So this was all about our cycloalkanes and cycloalkenes. In our video we have discussed about the method of preparation, their chemical reaction, their conformers and their stability. So thank you all for watching.